After studying this module, you shall be able to know the rules utilized in writing the electronic configurations. Also, you will recognize the need and use of various quantum numbers. You can identify the various possible states and microstates associated with the various multi-electronic systems. Introduction. The chemical properties of the compounds depend on the electronic arrangement of the atoms within. The electronic cloud is sectioned, which can be represented by the electronic configuration and orbital notations. When we are talking about the multi-electronic systems, the interaction between the various electrons will specify the various electronic states which are feasible for the electronic transitions to take place. In order to find the possible transitions, the various energy levels according to the different orientations need to be specified and arranged in the order of their energy.
We will discuss the electronic configurations of various species. First of all, we will look down the rules for writing the electronic configurations. There are certain rules to be followed in order to write the electronic configuration and orbital notations for various electrons of an atom. These rules can be specified as: the first rule is the Aufbau principle. The electrons in orbitals are always filled according to increasing order of energy. This is the Aufbau principle. It has been shown in figure. It means that the orbital of lower energy will be filled first, and then the orbital of next higher energy will be filled. To specify the trend, the chart can be considered. The diagonal rule is followed to find the increasing energy terms. In order to find the energy of the orbitals, their n plus l values should be determined. The orbital having lower n plus l value is of lower energy, and if the value is same for any of the two orbitals, the orbital value with lower n value will be lower in energy. The n and l value specifies the first principal quantum number, and l specifies the azimuthal quantum number. Both of these quantum numbers will be further discussed in the later part of the section. Figure 1 shows the increasing energy level followed up in a shell. For example, if we have to fill the electrons in shells, first of all, 1s orbital will be filled, next will be 2s, and then 2p, 3s, 3p, and so on. The next is Pauli's exclusion principle. It states that any two electrons present inside an atom cannot have all four quantum numbers identical to each other. An orbital can only grasp up to two electrons to the maximum extent, and each electron of the orbital should have an opposite spin. If the spin of one electron is parallel, then the other electron should be anti-parallel. The next to be discussed is Hund's rule. In an orbital, the electrons are first singly filled, and when all are singly filled, the pairing can take place. This happens because the most stable arrangement of the electrons is the one with maximum number of unpaired electrons. This leads to a minimum electronic repulsions and hence will lead to the stability. For writing the electronic configuration of the atoms, the above rules should be. The main energy level of an atom contains a total of n subshells, where n is the main energy level. The subshells are named as S, P, T, F, G, H, and so on. These small alphabets are originated from the words sharp, principal, diffusive, fundamental, used to describe the spectral lines of the hydrogen atom. Each increasing number of subshell has odd number of orbitals available. An S subshell can sustain a maximum of 2 electrons. A P subshell can have 6 electrons to the maximum extent, and D has a total of 5, and F has a total of 7 orbitals, and thus the total number of electrons which can be occupied by D and F is 10 and 14. Next, we will discuss the quantum numbers. First of all, why we need quantum numbers? It is required in order to completely describe the position of the electron in an atom. 4 quantum numbers are required, which can be named as: the first one is the principal quantum number, represented by the small alphabet n. Next is azimuthal quantum number, represented by the small alphabet L. Magnetic quantum number is represented by ml, and the spin quantum number is represented by ms. Sometimes spin quantum number is also represented by using small alphabet s. All the quantum numbers will be described separately one by one. First of all, we will move on to the principal quantum number n. The principal quantum number n tells about the basic energy level and distance from the nucleus for the given electron in an atom. It tells about the main shell of the electron. The higher value of n means more amount of energy involved, which further suggests that the electron is present farther away from the nucleus. Also, it is noteworthy that the levels of energy get even closer to each other as the distance from the nucleus increases. This is represented in figure, which shows the increasing energy levels of n in the shell. The next quantum number to be discussed is azimuthal quantum number, represented by the small alphabet L. It tells us about the subshell or the orbital in which the electron is present. The subshell informs us about the shape of the electronic cloud present. It also suggests about the number of nodal planes in the electronic cloud. These orbitals are the volume or space around the atom which electrons occupy 90 to 95% of the time. Each subshell has a number, form, and a letter correlated with it. The outline of the electronic cloud in actual practice represents the prospect of locating an electron in that spatial environment of the atom. In the case of an s orbital, the value of L is equal to 0, which represents the shape of a spherical shell. The value of N increases, the principal energy shell increases, and related to it, the size of the spheres also become larger and larger, but the shape is still the same. This has been described in figure. For a p orbital, the value of azimuthal quantum number is 1, representing the general form of a dumbbell or a peanut shape. A total of 3 p orbitals are there per principal quantum number n, which can be represented as px, py, and pz as their lobe orientation along the three axes. But the basic shape of the orbital is same for all the three. This has been shown in figure. It has one nodal plane, which is a space of zero probability of finding the electron. For a d orbital, the value of principal quantum number is 2, and there are a total of 5 d orbitals per n level. The first d orbital appear in the n is equal to 3 principal shell. Two types of shapes are there for a set of 5d orbitals. 3 are dumbbell shaped or can be said as clover leaf shaped. They comprise of two nodal planes, bisecting the probability twice, giving the shape of clover leaf. The fifth one has a peanut shape or a donut about it. The orbitals recline straight on the Cartesian axis or can be said as rotated 45 degrees from the axis. The 5d orbitals are named as dxy, dyz, dxz, dx square, y square, and dz square. The 5d orbitals are represented in figure. Now, for an f orbital, the value of L is 3. The shapes get quite complex. Imagine bisecting each of the clover leaves above through the middle again. The first f orbitals appear in the principal quantum number with the value 4. The f orbitals encompass the most intricate shapes. There are 7 f orbitals per n level. The f orbitals have very complex names. All the 7 types of f orbitals has been represented in figure. The next to be discussed is the magnetic quantum number ml, that basically specifies the different orbitals possible that are associated with the value of L. The orbitals suggest the orientation of the electronic cloud around a central point called the nucleus in the x, y, z plane. The total number of orientations feasible is based upon the subshell or the value of L. The value of ml can vary between plus L up to minus L. Now, if the value of L is 0, there is only one value of ml possible, and that will be 0. It means only one orientation of the electronic cloud is probable around the nucleus. The fact can also be verified since the shape of an s orbital is a sphere, and no matter what way we turn it, it will still be a sphere. There will be no difference, as can be seen from figure. For the value of L is equal to 1, the orbital specified is p orbital, which can have three orientations by the rule. The value of ml will be equal to -1, 0, and +1. This means there are three possible orientations of the electronic cloud around the nucleus. This has been shown in figure. Similarly, for the value of L is equal to 2, which specifies a d orbital, we have a total of 5 orientations possible, with the ml values -2, -1, 0, +1, and +2. This has again been shown in figure 5. Now, for the value of L is equal to 3, an f orbital can have 7 orientations, namely with the ml values -3, -2, -1, 0, +1, +2, and +3. The next quantum number we will discuss is spin quantum number, represented by S or ms. It is the last thing we need to fully describe an electron in an atom. This means to know that which way it is spinning on its own axis. The electron can either spin clockwise or anti-clockwise. Likewise, the labels are plus 1 by 2 or minus 1 by 2. As can be seen in figure, when the electron spins clockwise, it is given the ms value of plus 1 by 2, and when it is spinning anti-clockwise, it is given the value ms equal to minus 1 by 2. But we cannot say in which direction, whether clockwise or anti-clockwise, the electron is going to move. Till this point, we have discussed the quantum numbers for the single electrons. Now we will discuss the quantum numbers of multi-electronic atoms. The quantum numbers for the single individual electron can be easily stated, but in the case we are talking about a system of electrons as a whole, the quantum state becomes somewhat difficult to describe since now the electronic interactions play a major part. Because of the electronic repulsions, the electrons tend to occupy separate orbitals. Hund's rule of maximum multiplicity and also the interactions lead to parallel spin of electrons in different orbitals, which actually enhances the exchange energy. In order to understand the various electronic interactions, let us consider a system of carbon atom having two electrons in the last orbital. The electronic configuration of the atom is given as 1s2, 2s2, 2p2. For the valence electrons, we have the set of quantum numbers. N is equal to 2 and thus the value of L is equal to 1. From the value of L, it can be depicted that we can have three values of Ml which are +1, 0 and -1 respectively. Thus, Ml should be equal to +1, 0 and -1. The value of spin quantum number can take up two values where ms can be plus half or minus half. Each of the 2p electrons can have a set of ml and ms values with various combinations. The 2p electrons are not autonomous with respect to each other, since their orbital and spin angular moments interact together by Russell-Saunders coupling phenomena, which can also be called capital S and capital L coupling. It is said as LS coupling. By the interaction are produced new quantum states for the system, which are termed as microstates. A new set of quantum numbers is then used to describe this new quantum state of the system. The new quantum numbers are then designated as capital ML and capital MS, which states the total orbital momentum and total spin angular momentum of the system. Capital ML is equal to summation of small ml values. Similarly, capital MS is equal to the summation of small ms values. Now we will tabulate the various microstates possible according to their ml and ms values for a P2 case where we can get a total of 15 microstates. The notation 1 plus signifies that the electron is having the value of ml is equal to 1 with the spin value of plus 1 by 2. On the similar terms, the microstate table can be constructed. The microstate table for the P2 configuration has been shown in figure. It can be seen that no two electrons can have the same identical quantum numbers, as well as we can count only the unique microstates possible. The microstate tables shows the various values of ml and ms. The notations for the first electron are Ml equal to plus 1, Ms equal to plus 1 by 2, which is represented as 1 raised to the power plus. For the second electron, the value of Ml is equal to 0, Ms equal to plus 1 by 2. It is represented as 0 plus. The microstate here can be represented as 1 plus 0 plus. The quantum numbers ml and ms further determines the value L, S and J, which are atomic quantum numbers. The difference between ml, ms and L and S is clear. ml and ms represent the microstates themselves, whereas L and S is the collection of microstates. Capital L and capital S are the largest possible values of ml and ms. According to the values of capital L, the atomic states of the system can be capital S, capital P, capital D, or capital F. The values of capital S are used to find the value of spin multiplicity represented by the formula 2s plus 1. The values of L and S are called free ion terms because they describe individual atoms or ions free of ligands. The free ion terms are very important in the interpretation of the spectrum of the coordination compounds. These terms also interpret the energy and symmetry of an atom or the ion and determine the possible transitions between states of different energies. Now, in order to reduce the microstate table to its constituent atomic terms, first of all, we have to look for the terms for the largest ml values and associated with it the largest values of ms. By this means, we get three free ion terms represented in the microstate table in figure. The three terms triplet P, singlet D, and singlet S specify three distinct energy states with different electronic interactions. In figure, there is calculated free ion terms for the P2 configuration. The largest Ml term is plus 2, so the value of capital L is equal to 2, which suggests a capital D term, and since the ms value is 0, it suggests the ml value of plus 2. 2s plus 1 gives us the value 1, which is s is equal to 0. Thus, the term comes out to be singlet D. The next largest term of ml is plus 1. So, the value of capital L is 1 corresponding to a capital P term. The value of ms is correspondingly 0 and plus minus 1 for the ml value of plus 1. This gives us 2s plus 1 value of 3, giving us triplet P term. The remaining microstate ml is 0, suggesting an s term with ms value of 0 for ml equal to 0 and 2s plus 1 now gives the value 1, suggesting singlet S state. Out of the three terms, the lowest energy term is the one with highest spin multiplicity. In this case, triplet P is the ground state term. If in any case we have two states with same spin multiplicity, then the ground state will be one with the highest value of capital L.
Summary. The chemical properties of the compounds depend upon the electronic arrangement of the atoms within. In multi-electronic systems, the interaction between the various electrons will specify the various electronic states which are feasible for the electronic transitions to take place. Aufbau principle states that the electrons in the orbitals are always filled according to the increasing order of the energy. Pauli's exclusion principle states that any two electrons present inside an atom cannot have all the four quantum numbers identical to each other. Hund's rule says that pairing of electrons in the orbital will never take place unless each orbital is individually singly occupied. Principal quantum number n tells about the basic energy level and distance of the electron from the nucleus in an atom. Azimuthal quantum number L tells about the subshell in which the electron is present. Magnetic quantum number, represented by ml, basically specifies the different orbitals possible associated with the value of L. The orbitals suggest the orientation of the electronic cloud around the central point called the nucleus in an x, y and z plane. The number of orientations feasible is based upon the subshell or the value of L. Spin quantum number ms is needed to fully describe an electron in an atom. This means to know that in which way it is spinning on its own axis. The electron can spin either clockwise or anti-clockwise. The electrons are not independent of each other when we are talking about multi-electronic systems, since their orbital and spin angular momenta interact together via Russell-Saunders coupling phenomena, which is also called LS coupling. By the interaction of electrons, there are produced new quantum states of the system, which are termed as microstates. The new quantum numbers are then designated as ml and ms, where m is capital, which states that the total orbital momentum and total spin angular momentum of the system is represented by the formula capital ML is equal to summation of small ml and capital MS is the summation of small ms values.